director in the back here. Okay, so we're here for another week, right? We're here for another week, and let's see, next week you guys are going to have, what, 5 exams in this class and 3 quizzes? No! A little bit of time off coming your guys' way, right? So speaking of quizzes, I was going to come up with some cool excuse to make myself sound awesome, but I just forgot to put the quiz up for you. Whoops! It's been a little bit of a busy weekend for me, so we'll have one. We'll have one this week on the beginning of the tail end of the equilibrium part there, a little bit into the acids, right? So the beginning of the acids part, the tail end of the equilibrium stuff there. We'll have a little bit of a quiz on that. And we'll probably have it on Wednesday or something like that, right? Yes, assuming I don't forget again. But anyway, we'll make it happen here. And don't forget your exam corrections today by, what I say, 5:45, yes, right? So if I'm not in my office, I should be around. If I'm in my office, leave me in a little box that's right outside my door. Okay? Cool. What's up?
What if you come like baseball skating down the hallway at 5:40?
5:45, it's due, right? I'm going to be very strict on this, right? So, anyway, so we have that. I think, or at least Dr. Tong informed me there was some shenanigans with the lab schedule. Did he send out an announcement to you guys about this? Nothing? No? Maybe?
It's just we have lab, you probably didn't.
Yeah, but okay, as long as you guys are, as long as you guys are aware.
Surprised by the fact that we have lab this week.
Man, as soon as he becomes department head, he tries to change the entire university schedule. All right, so now we're gonna do lab or not. All right, but anyway, so as long as you guys are aware of that, and then hopefully we'll get that taken care of, right? All right. Let's see what else. Let's see. We should be maybe finishing up at least the lecture slides from chapter 17 today. Maybe we'll go a little bit over. It'll just kind of depend. We're like I'm not in a huge rush. I'm just letting you guys kind of get an idea of where we are. And then, as usual, as soon as we finish the chapter, we'll start to do a little bit of practice problems for a day or so afterwards, and then we'll move on to the next part, which will look very similar to this, especially towards the tail end of what we're doing. And what we'll be talking about today, right? So we'll be, like I said, we'll be in this chapter, or these concepts of equilibrium for about 3 chapters here then. And then, what is the week after you guys get back? Exam 2, correct? Is that what it is? I forget. I think that's what it is. That sounds right to me. That seems about the time it would be. 16th.
It's the week after.
Okay, there it is. Cool. So then we'll have exam number 2. Exam number 2 weeks after. Oh man, I got so much information I can just cram into you guys and make it really, really difficult and really. I'm just kidding. It's a bunch of case stuff, right? So, but as usual, right? It'll be a little bit kind of tricky with what we're asking these kind of things, right? But that's okay. We got time to practice. Let's see what else I need to chat with you guys about. See, we took care of the quiz, kind of where we are in class, and kind of these other kind of things here and there. So I think that's all I needed to chat with you guys about. So let's get started with some prayer then, and then we'll see how far we get today with this. But Lord, we just thank you for another day and another week, and we just thank you for this beautiful day that you've created for us, Lord, with the bright skies and the wonderful weather that we're able to enjoy here, Lord. We just pray for the people in Texas and everyone who's just kind of affected by the winter that's been going on. Lord, we just pray that your hand be over them, Lord, and just protect them and guide them. Lord, we pray for the people that we encounter today. We pray that we can just see them with the eyes that you have for them. And we pray, Lord, that you can just open our hearts to those around us, Lord, and that we can share you with them in whatever way that might be. We just pray all this in your name. Amen. All right. So, I'm reminded, or I just reminded myself that I was in the, don't worry, this is another one of my dumb stories. I was in my office this morning and I spilled vanilla on myself. And so now, like, every once in a while, I just catch a waft of myself. Well, I smell like a walking bakery, which isn't too bad of a smell to have, but, it just, I'm like, oh yeah, I'm still pretty hungry. So, anyway,
What time do you get to work, Doc, to have time to dump vanilla on yourself?
Usually around 3 or so.
What?
Got stuff to do, right?
When do you sleep?
At night. Anyway.
3 a.m. this night.
Yeah. Anyway, so here's where we ended up, right? So we were here and we were learning how to get pH from our Ka, right? And so we were given a concentration of propionic acid, which is one of our organic acids, which is a weak acid. And we were asked to figure out the pH from this, and we have to set up an ice table, and we have to figure out what our X's are and all that same kind of stuff that we've seen over and over and over and over and over again. Real quick though, let me back up for just a minute. How do we know that this is a weak acid without me telling you guys?
Because it doesn't completely dissociate.
No, that's what, I mean, that's true, but how do we know that this is a weak acid?
Because it's not one of the 6 we had to memorize.
Okay, that's always useful to kind of keep in mind, right? It's not one of our 6 strong, and this is not there. How else? Yeah.
Because of K, it's like, it's pretty small. So.
Yeah, right? So always paying attention to the information that you guys are given, the numbers that you guys calculate. What are you trying to get from that, right? Like our K is not just a number for us to plug in and make ourselves feel miserable because we have to do math, right? It tells us something, okay? It has a practical application to it. And so here, if we have something times 10 to the negative 5th, right, that means we're heavily reactant favored, so it's not going to dissociate all that much. Got it? That tells us a lot of information because this question asks us what percent is ionized, aka what percent is dissociated, essentially, right? So we know we should be getting some kind of small numbers as we go through. You guys with me on this? Right, so we set up our equilibrium. I think I left you guys with this. And you guys all groaned in unison as you realize that what? You have to solve a quadratic, right? Crap. So we set up our quadratic. We pretend to put in our calculator. We give up. We go online, right? Right? So real quick here. So whoops, I already got all that stuff here. So if we kind of simplify everything, I got x squared plus 1.4 times 10 minus 5x minus 0. Yada 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 1 4, right? 1 2 3, right? So there's our equation that we have to solve. That equals 0. I can write a 0. That'd be good. There it is. Okay. Good. So we plug that in, and I got x equal 0.00 0.00117, right? Good. And then we can plug that in, we can get the information out of there, right? What's this thing asking? It's asking the percent of acid that's ionized. So what does that mean, right? What does that mean? It means how much of our initial stuff, right, turns into this stuff over here. Got it? You guys with me on this? Just how much dissociates. Well, how are we going to figure that out? Well, we know how much we started out with, right? And we know how much of the anions we make. So how could we figure out the percent of this?
Part over whole?
Yeah, that's it, right? Just x over the 0.1 there, right? You guys with me on this?
No.
So this is how much is dissociated. This is how much is ionized. This is our equilibrium expression, right? Our equilibrium concentration for how much of our stuff is bouncing back and forth. You guys with me on this? It could ask this a different way, maybe. It'd be kind of not a true way of asking, but it's a, you know, what percent of our product exists if you want to think about it in that way. You guys with me on that? So we just figure out our x divided by our total number that we started out with. Yeah, what's up?
And we're dividing by 0.1 because that's the molarity of
That's what we started out with, yeah. How much of that turned into the A minus is basically what it's asking. Yeah.
pH is log 10 of log base 10 of
Negative
what?
log of.
Negative log
yeah.
of what?
Hydronium ion. Good? So if I believe I have some space here, let me put all these ideas together. Okay. So x is equal to 0.00117. So our pH, right, one thing, negative log of our x, right, which I got to be about 2.93-ish, right? And then our percent ionized equal to x over our 0.1, right? Our total that we start out with times 100. Put it out about 1.18%. Good? All right. So, question that I already know the answer to, right? So point number one, whenever you're in a discussion, don't ask a question that you already don't know the answer to, right? Right? How many of you guys enjoy solving things with the quadratic equation? Good, that's what I thought. None of you guys, right? So let's think about this for just a second, once more, okay? So we're back here. What does x represent?
The death of our hopes and dreams.
Those are both great ways. I like it for that, for sure. Right? I get to buy lots of red ink pens or multicolored pens, right, to take off points. It's great. But what else?
Concentration of hydronium ions.
Okay, it tells us our equilibrium concentrations of things. It tells us how much gets changed in between there, right? But what do we notice about our answer for x? Pretty darn small, right? Is there a big change in the concentration of things? No. How do we know that? Is that unexpected?
No?
Why do you say no?
It's a weak acid.
It's a weak acid, and what is that? What's our Ka?
Small.
Really small. Got it? If it's really small, we don't expect there to be a big change in our concentration. Are you guys with me on this so far, right? Our Ka is times 10 to the negative fourth. Our initial concentration is pretty high, 0.1, right? There's a gap of what? About times 10 to the negative 4, about 10 to the 4 in between our Ka and our initial concentrations. Everybody still with me on this? So what does that mean? That means we've got a pretty large concentration to begin with, and not much of it is going to change because we have a small Ka. Right? Does that make sense? So what does that mean in terms of our x? What does that mean in terms of this factor at the bottom here? How could we approximate this value at the bottom?
0.1.
Just by using 0.1. Is everybody following along with this? Here's what I mean. Take 0.1 minus this. What do you get? 0.99, right? 0.998 something. What is 0.998 something really? 0.0998 something, right? What does that equal to? Essentially equal to what? 0.1. So, do this real quick. So, drop the x here at the bottom and solve for your new x. Tell me what value you guys get for that. Assume x is a small change. Assume there's a small change. So we can simplify to avoid doing a quadratic and tell me what x is equal to then. What'd you get? So if you do the simpler math, what does x come out to be? 0.00118 is what I got instead of 0.117, right?
I got 8 the first time doing the whole thing too.
Yeah.
So it's literally the
Yeah. Do you guys get the point that I'm making here then?
same. Yes.
So would you guys rather do it the easier way or the quadratic way? Well, the answer is we want to do it the way to get to the right answer, correct? That's really what the answer is. Now, how can we eyeball these things? How can we make sure it's safe to do the shortcut? Well, really what you have to start to pay attention to is what your initial concentration is and what your K is. If you see a gap of about times 10 to the 3 times 10 to the 4 in between there, you're probably safe. Right? If there's a massive gap in between it, you're good to go. You can drop that x out of the bottom and simplify the expression. Okay? You guys with me on this? Is it always going to be like that? Well, no, but like I said, that's a good approximation. That's going to work for us, about 99% of the time, right? If we have that, if we see that gap of about times 10 to the 3, 10 to the 4 in there. Okay? And there you go. You guys proved it to yourself. You did it the long way and you got 0.0017. You did it the short way and you got 0.0018. So there's really no difference in between the two. For all practical purposes, right? All right. Yeah, we can assume all these are aqueous, right, especially if we've got water as part of it. Yeah, we'd have to do different stuff if this wasn't in water. it's a little bit different than what I got. Yeah, practically nothing, right? This one's referring to the, you know, the
Okay.
base dissociation, right? Yeah. Cause I got 0.59, I believe is what it was.
Okay.
Yeah. I mean, everything else it looks like you set it up right, so I don't know if it might just be a calculator issue or not. Did you get something different? No. I don't know, so the calculator I use sometimes gets dumb when I put the exponents for the times 10 in there. It sometimes does the math up there rather than doing so. That might be, that's a common issue there running into. Cool. So now figure out the pH. Right? Oh, you got it there. I didn't even see it. Okay, good. Excellent. This, you're assuming that this is going to be the concentration of the hydroxide, but you have to figure out the equilibrium concentration of it. So you're gonna have to set your ice tables and do that kind of stuff again.
Doc, to find pH, don't we need to, since this is the base stuff, don't we need to subtract our answer from 14 to get the pH?
Here you go. You
So
got
the
it.
pH is,
You can speak up. It's okay.
well, then I give everyone else the answer.
Well, now you're on the spot. Now they're all looking at them, right? They're all watching.
11.78.
That sounds better. So, when you're setting it up for, right, you're using the equation the way I have it written up for you over here, right? So this, right, this is your initial, right? And so then you have to figure out the equilibrium concentrations of these there, right? So you're approaching it the same way, right? It's just that this is how we're looking at the base side underneath. That's all it is, right? But practically, there's no difference in between. Cool. So you got simple you can make the assumption you guys have the X on top, or that's what you do.
Cause like we have this equation.
Or you can do the quadratic.
Yeah.
Oh,
RC.
what?
How can you subtract it by 14?
Because we found the thing with the base, pH is for the acid.
Oh, I see, our K, that was our KB.
Yeah.
Asking for pH, not POH, so do we still need to subtract?
Because, yeah, we're
Well,
given the equilibrium.
if you're finding Ka, then your negative log is your pH. If you're finding Kb, then that's your pOH. So you need to subtract one from 14 to get the other.
So like the calculation that we did, like the negative log of 0.00595,
Oh.
that's the POH, not pH.
Yeah.
So
So
just
then you
multiply this,
subtract that
multiply that
number
times that,
from
and then take the
14,
square
and that
root.
gives you your pH.
Okay.
There might be a calculator issue sometimes. What I've noticed is like different kinds of calculators are just really dumb when it comes to like orders of operation. And that's where like if you try and throw the whole thing together, sometimes they're just like, I'm not gonna do it properly. So for the way I solve everything on my calculator is one instance at a time, right? I multiply the stuff, then I take the square root and say, let's put it all together. It takes longer, but I don't see those mistakes happening, is the only difference. Yep, looks about good. All right. You want to do the quadratic?
Okay.
All right. Okey-dokey. So it's a big surprise, we have to set up an ice table. I can tell from your stunned silence that you guys are shocked at this, right? You know, it's very, very new. Okay?
What if we skip that step?
Then you're gonna run into problems. The whole point of doing practice is that when you get to the exam, you're gonna do it the exact same way, right? If you skip steps here, then you skip steps on the exam. Okay. Okay. Now, nothing different here, right? Kind of looks the exact same thing that we set up. What's practically the only difference between KB and KA? One's looking at it from the base side, one's looking at it from the acid side, right? Does it change any of our math? Not really, right? The only difference is we typically report things in terms of pH, and from here we can figure out pOH, so we just have to add that last bit on at the end there, right? But practically speaking, there's no difference. So we set up our K, right, so instead of -4, right? X products, X times X at the top over our reactants, 0.06 minus X, right? Products over reactants, everything to the exponents of 1, right? Because everything's in a 1 to 1 to 1 to 1 ratio. That's good, that's important to remember. We could solve for X going through the quadratic. I went ahead and did that for you guys. So quadratically, I think that's a term. 0.00566 is what I got when I got it out of the quadratic equation.
What if we use the shortcut?
Yeah, okay, if you use a shortcut, right? Remember our thought process is in the shortcut, we're not gonna change the initial concentration here all that much, right? So we can leave the X off the bottom so we can avoid the quadratic, right? And I think I saw everybody doing that in here, right? Well, I think one person was doing the quadratic, I saw that, right? Going the extra mile. So if we do the assumption, right? If we work through our assumption, I got X is equal to 0.0059, right? So a little bit of a bigger difference here than what we saw last time, right? 0.0056 versus 0.0059. We have to be careful here. There's another, what's the word I want to, what's the phrase I want to use here? There's another check you can make, right? The bigger the difference between the quadratic and the actual, then, you know, we're going to have to go through and solve it quadratically, right? And I think kind of the rule of thumb for that is if you have anything that's bigger than like a 5% difference or a 10% or anywhere between 5 and 10%, you kind of have to go through the quadratic route there is what it is. Now, what's the problem with doing that kind of check? Well, you have to do the quadratic anyway, got it? So you might as well just use that, right? But, you know, that's the other kind of end of things here, right?
So you're saying the shortcut can be used, but it shouldn't be used?
No, I'm saying with any, as with any shortcut, right? As with any shortcut, you're always leaving something out, right? That's the whole idea of a shortcut, right? There's always something you're gonna be missing. And if you just willy-nilly use it and you're not paying attention, then you are gonna run into a problem where you didn't check your initial concentration and you didn't check your initial K, and they're gonna be too close together and you're gonna shortcut it and get the wrong answer is what it is, okay? So always be careful of that. Cool, all right, so either one you wanna use is just fine, right? But if we solve that out, right? We got our X equal to about 0.0056 or 0.0059 there, right? To get my pOH, I take the negative log of X, right? And I've been skipping over this, but let me just draw this point again here, right? Remember, our X represents either our hydronium or our hydroxide concentration, depending on the equation that we have set up, right? So when I'm taking my negative log of that, that's my pH, my pOH. Right? Don't forget that part, okay? So I plug that in, I got my pOH equal to 2.23 is what I got. Right? Here's another point where I'm happy, I got a reasonable answer, I pat myself on the back and I move on with life, right? If I didn't ask for pOH, I asked for pH, right? So don't forget, pH plus pOH equals 14. Good? Yep.
Is it ever possible to have an acid with to go past the bounds of 14 or 0?
Not really in aqueous solutions, right?
So
Numerically, yeah, you can, right? But not for anything that we're really gonna run into, right?
What about solids or gases then?
Sure, but then we're dealing with different stuff, right? What's up?
So the X was the X you found when you put in negative log?
Yep. right? So remember, X represents our OH concentration, right? That's what this column over here, and I just plug that in there, and that's what I got. Literally just type negative log into the calculator, is all it is, right?
I don't know if other people feel this way. I'm like still kind of confused, like algebraically, how you find the x if you don't do the quadratic equation.
So how to solve for X if we just simplify it?
Yeah.
Sure, yeah, I can show you guys real quick. So, whoops. 5.9 times 10 to the minus 4, right? If we take our simplification, we have x squared over 0.06, right? So I just drop that x factor out of the bottom there, right? So then I just rearrange and do 0.06 times 5.9 times 10 to the minus 4, right, equal x squared. Right? I don't have these numbers written down for me, right? So I can't tell you guys that real quick. But if you take the square root of that expression, then you solve for x that way. Okay? Cool. All right. I think I gave you guys all the answers here. Oh, we forgot to mention the pH. So let me scroll back up. If the pOH is 2.23, and so pH plus 2.23 equals 14, right? Then my pH I got to be 11.77. All right. Ooh-wee. You guys starting to notice any patterns with how we solve things in here? How we set up our ice tables, how the X's kind of fall out, all these kind of things? I hope so, right? If not, it's okay. Keep looking through some more problems, start to look for the patterns for how you solve these things, okay? Yes?
The shortcut can only be applied to each acid, is that what you're saying?
No, it can be applied to any equilibrium, right? Any equilibrium where you have a sufficient difference in between the initial concentration and the K, right? And so that's what I was talking about earlier here, right? So what I'm looking at is, what is the difference in the scale of those two values there, right? So if there's a difference of like 10 to the 3, right, there's a difference about 10 to the 3 in here, that's pretty darn close to cutting it, you know, to not having, or not being able to do the shortcut. But 10 to the 3, 10 to the 4th and bigger, that's just fine. What's up?
What does the P and pH stand for?
Negative log.
It doesn't stand for any word?
No, it's a mathematical expression, right? A mathematical function. So you can take the negative log of tangerines being eaten in the classroom. So negative log of 1 is, no, 1/2 now, right? Right? Yes?
But that's only of like the total concentration. That's what you're
I'm
looking
sorry,
at?
of what?
To like compare the differences between K and the total.
Yes, yeah. That's just, yeah.
How did you know to like use pOH instead? Cause like,
Yeah, great question, right? Because there's, oops. So, there's no H3O plus anywhere here, all I have is OH, right?
yeah.
So if I'm calculating the concentration of OH, then it follows, I can figure out my pOH,
Okay.
right? So taking a look at whether you're dealing with bases or acids is gonna be important, yeah.
Could we also just phrase that as if you're finding KB, you're finding, pOH, and if you're finding Ka, you're finding pH?
Most of the time, that's what it's gonna be, right? But that's saying the same thing, right? If I'm dealing with acids, then I have, I'll have H3O plus as part of my equation, right? So. Good?
So acids can be gaseous?
Yeah. HCl is technically a gas until you bubble it through water, then you have the hydrochloric acid, right?
How corrosive are they in gaseous state?
But, more corrosive usually, right? Gases tend to be more reactive just because of, well, I gotta be careful there. I guess, no, I think that's a fair statement. Yeah, gases tend to be more reactive, they're just kinda, there's no surface area issues, right?
So is that
There's
why
no
like if you
mass
inhale
transfer.
chlorine gas, it like liquefies your lungs and you drown there on lungs?
What? Why? I mean, yeah, don't do that, but what's your question now?
Is the corrosiveness of the chlorine gas like the cause of that?
Well, that has nothing to do with its acidity, right? That just has to do with the inherent reactivity of chlorine gas, right? Chlorine gas is not HCl, right? Chlorine gas is Cl2. Right? Okay, so how can we relate then Ka to Kb? And I think this might be a little bit of what you were asking there earlier, before we talked about liquefying our lungs. So if we have our expression for Ka and our expression for Kb, right, which is just these two components here, right? If we multiply those two together, Ka times Kb, right, we can simplify everything to get our expression for Kw, which is what we were talking about earlier, right? So if you guys are following along, A cancels out with A, and let's get a different color, HA cancels out with HA then, right? You guys with me on this? Right, so it's what we were mentioning earlier, right? And that's equal to Kw. Kw is our equilibrium expression for the dissociation of water, right? Yeah.
Is A the conjugate base?
Yep.
Okay.
Yep. So you lose H plus, you get A minus, right? Cool, so there we have a way of, or we talked about that earlier, right? We have a way of relating hydronium to hydroxide concentration as long as we have our expression for Kw, right? Now, remember, right, when you're dealing with Kw, it's an equilibrium expression, so we have to pay attention to the temperature that things are reported in, right? So don't forget about that, right? Kw at room temperature is 1 times 10 to the negative 14th, right? All right, so if we have a question like this, right, and we have a compound, who cares about the name or the formula? If we say it's a weak acid, okay, right, and then we're asked to calculate the Kb for this, right? So basically this question is, how can we calculate Kb if we have Ka, or how can we calculate Ka if we have Kb, right? What's up?
So what you're saying that Kw is a constant that's at room
All
temperature?
Ks are constant.
Okay, so at room temperature, Kw is always equal to 10 to the negative 14?
Yep. Right.
Thank you.
Mm-hmm. Right. So now, if we want to be super duper tricky and confuse everyone, right, we can start to talk about the pH and give you guys a deal with bases and pKa's, and all, right? Anyway, the point that I'm trying to say is we can relate Ka's and Kb's, we can relate pKa's and pKb's, we can relate pH and pOH, right? So we're starting to get a lot of different equations to come in here to express different parts of these problems and these reactions, okay? Everybody following along with this? There's multiple ways of getting different information, different values out of these ice tables and these X's that we keep calculating. So what we have to do is make sure we got it all straight in our mind here, what each one of them represent and when and how it's useful to use those. Yeah?
How is Kw useful?
Kw relates Ka times Kb, and if we follow through, we can also get our pH and our pOH from that, right? Because if we take the negative log of that expression, we get pH plus pOH equals pK, the 14, right?
Okay.
Good? So nothing too tricky here, right? Ka times Kb, and we just plug in the appropriate numbers after we rearrange them. Good? All right, so what is this telling us again, right? Just, it's always useful to kind of step back and take a look. We define it as a weak acid, we have a Ka times 10 to the negative 10th. It's a pretty weak acid, right? Something's going to 10 to the negative 10th, and water is an extremely weak acid. And so we should expect that the Kb is going to be higher than our Ka, right? So that's always something else to come back and double check your math in case we have a calculator issue somewhere, right? If you have your Kb that's smaller than your Ka, then it looks like something got reversed along the way there, right? So just be careful of that. All right, so now let's talk about what happens a little bit when you mix these acids and bases. Now, some of this stuff we already talked about in Gen Chem 1 when we were talking about our aqueous reaction chapter there, where we talked about our precipitations and we talked about our redox reactions and what else did we mention? We talked about decompositions and metathesis reactions and all these kind of things. The double displacement, sorry, the double displacement reactions, right? So We talked a little about acid-base and neutralization reactions in that chapter there, right? So this is kind of more of the same, although now we're stepping back, and instead of just, let's say, doing the stoichiometry for neutralization, we can start to take a look at the equilibrium expression and measure the pH of neutralizations, okay? All right, so remember whenever we have the word salt or whatever it's typically used in the book, right, we're just talking about ionic compounds, right? So the generic expression for a acid base is your acid plus base goes to make salt plus water, okay? And that's what we learned in the first semester of Gen Chem, right? How to determine what our acid and our base are and how to figure out what our salt is, right? We broke those apart, we brought them together, the negative comes together with the positive, right? All these kind of things. Okay? So now we're going to take this idea of these acid-base reactions and start to kind of break them apart into a couple different groups, okay? I think we're going to talk about 4 groups. What happens when you have a strong base and a strong acid? What happens when you have a strong acid and a weak base? What happens when you have a weak base and a strong acid, and then weak acid and weak base? Got it? So we're just kind of systematically changing one thing from weak to strong is all it is, okay? This is going to be important because it's going to change, right? Being able to recognize it's going to change the math that we need to do to solve these types of problems. Being able to recognize weak versus strong, okay? You can do it by looking at your Kas or your Kbs, or you can look at it by, what is the specific acids and bases that are given to you guys, right? So HCl is one of our 6 strong, right? HCl, HBr, HI. Those are 3 hydrogen halides that are strong. Here we've got a ionic compound with hydroxide in it. You can pretty much make a safe bet that any hydroxide containing compound is a strong base, right? So we got HCl plus NaOH goes to make sodium chloride, right? We take the plus from here, right? We take the minus from here, and that's where our sodium chloride comes from, right? We know we have to make water. That's all it really comes down to. Right? Here's our walkthrough that we did in Gen Chem 1 there, but we broke everything apart, we brought everything together, these kind of things. Okay? And here's our net ionic equation. That makes sense. Acid, right? Plus base goes to make water, right? That's all it is. Okay? The sodium and the chlorine don't participate. There are spectator ions. Now, this is going to be the key thing to pay attention to. The key thing to pay attention to is what is the nature of that salt. Because when you have something like sodium chloride, the sodium and the chlorine aren't going to be doing anything. They're just going to kind of be hanging out and making sure the charges are balanced and that kind of stuff. Okay? What we have to think about behind the scenes is that if you start out as a strong acid, okay? If you start out as a strong acid, you make a weak conjugate base, okay? Strong acids make weak bases. Weak acids make strong bases, okay? Now, I'm speaking in generalities, but it's an extremely important generality to remember, okay? Strong acids make weak bases. Weak acids make strong bases, and the converse is true also, right? Strong bases make weak acids, yada, yada, yada. You guys get it. Now, really, right, now that you guys have written it down, I'm going to make you guys use your erasers. Right? What I should be saying is the stronger the acid, the weaker the base. Got it? It's not just if strong acid, then weak base, right? There's a progression with these things, okay? But I'm giving you guys the phrase to put on your on your arm when you guys go get your tattoo, right? Weak acid, strong base, got it. You'll be laughed out of the tattoo parlor, but hey, if you guys have it for your exam, right? What am I going to make you do? Wear sleeves, right?
I asked Dr. Marsali if I could get the unit circle tattooed on my arm before the calc exam.
How long did he laugh at you?
He didn't laugh, he just
Oh,
stared at me.
no sense of humor. All right. So, all right. Anyway, right? So this is one of the first questions I ask you guys in organic chemistry also, right? By the way, who's going on to organic chemistry?
We have to pass this.
It's true, all right? So here's a little hint. I tend to give a quiz on the first day of OChem.
What?
On all the stuff that you guys should know that I keep reminding you of. right, in Gen Chem, right, you guys don't have to take it, is that right? Woo, all right. Right? So I'm telling you guys all this stuff that's going to be on this quiz, okay? And one of these important things to remember is the relationship between stronger acids and weaker bases and these kind of things, okay? But this is going to help us here, right? This is going to help us here because this is going to change the math and how we have to approach this. Everybody with me on that? Okay. So, extremely strong acid, HCl, makes extremely weak base, chloride, so it's not going to do anything else, right? All they're going to do is react with each other and then just kind of sit there in solution, right? That's all it is. And so that's what this slide here is kind of telling me, all right? So sodium chloride are spectators, they appear as reactants and products, right? So we don't care about them. The net products are a weak acid and a weak base. That's what I'm trying to explain there to you guys, okay? Like a really weak acid, really weak base, right? HCl is not that acidic at all, right? Not HCl, excuse me, water, right? H2O is not that acidic at all, right? It's not going to do anything, right? And so if we have an equal molar solution, right, we're going to end up with a neutral pH of 7, okay? That's all it is. Now be careful because what we're going to talk about as we move into the next chapter, we're going to talk about titrations and neutralizations. It doesn't necessarily mean that your pH is 7, right, after you're done with your titration or your neutralization. It depends on what type of acids and bases you're putting together. Okay, this is going to be the tricky part. I know as soon as you guys hear neutral, you're like 7, right? Well, I hope, right? Or 0, maybe, I don't know, right? But be careful with that, okay? Be careful with that. So we have to pay attention to what reaction we're doing, okay? All right, so equal moles generate a neutral solution in terms of pH of 7, right? Good? Okay. All right, so now we have a weak acid and a strong base, right? There's one of our quintessential weak acids is our good old buddy acetic acid, right? This one that we see over and over and over and over and over again, right? If we react that with some sodium hydroxide, okay, we make the conjugate base, okay? And if we have a weaker acid, we make a stronger base. And this is the key part, okay? That stronger base can go on to do something else. And that's where the math is going to come in, okay? I expect you guys should be able to do strong acid-base chemistry at this point. That's just balancing moles on both sides of the equation, okay? But as soon as we switch over to this weak acid or weak base with strong acid or strong base, then we have to start to bring in our K aspects to it. Everybody with me on this? Strong acid-base stuff is just Gen Chem 1, balancing moles. As soon as we put the weak stuff into there, then we have to bring in Gen Chem 2, which is where we learn about equilibrium, okay? I mean, there's moles in equilibrium, right? Right? But there's also ice tables and tiers, okay? So a little bit different way to approach that, okay? Anyway, here's the same thing. This, right? Our strong base completely dissociates, right? And we're ending up with our acetate ion there and water, right? So acetic acid plus hydroxide makes acetate and water, right? That's our net ionic equation for this.
So we're saying that acetate is
A stronger base. Yeah, so it's going to go on to do something after the acid and base react, is what it is. And I'll show you guys here on the next slide, right? Right? So acetate is a weak base, right? We should say, well, I think that's a fair way of saying it, right? It's a weaker base, but it's stronger than water, right? That's the kind of relative point that we compare everything to, so to speak, right? So how do we know this? Well, this is what I was telling you guys earlier. Weak acid makes a stronger base, right? Stronger than what should have been the question. Well, stronger than water, right? There's your answer to that one there, okay? But if we're with a weak acid, we make a stronger base. That stronger base is going to go ahead and then react with water, Got it? And when it reacts with water, it's gonna reform acetic acid, almost like an equilibrium, right? And make some hydroxide again. Got it? So what does this tell us? Well, we make hydroxide again, which means that our pH is going to be basic. It's going to be above 7. Got it? If we make a base, right, if we make a base, then guess what happens to our pH? It's going to be above 7. That's all it's saying. You guys with me on that? So now what's the question? Well, we identify a weak base that's in solution. So we have to use our K values to kind of figure all that stuff out. What exactly is going to be the pH? Got it? Because what is this equation here? This is our base plus water goes to make acid plus hydroxide. Or, as we just did previously, right? B minus plus H2O makes HB plus OH. Right? Our generic expression for our dissociation of a base. Right? What's up?
Just to make sure I understand this. So weak acid plus strong base ends in a basic solution.
Yes.
So would the reverse also be true, that a strong acid and weak base would end in an acidic solution?
What do you think?
I'm guessing yes.
There's always a balance to things, right? But always, we'll talk about it. Yep. So, here's a typical question, right? Or a question that's related with these kind of things here. Right? For a weak acid plus strong base, pH depends on the pKb, right? The larger the Kb, the stronger the base. That's all stuff that you guys know at this point, right? Nothing new with that. Right, so question, what's the pH of a 1.5 molar sodium carbonate solution? Okay. Now the reason why I'm asking you guys this question here is to get across the point that if you have, right, a solution with some weaker base in there, what's going to be the pH of it? That's all it is, okay? So I'm just giving you guys some information here about what's happening. Okay, so if we go through the whole rigmarole, there it is, right? Kb, product over reactants, the X, we can do our approximation. Right, we've got a huge concentration there, 1.5, right? That's a massive concentration, so easy to do this approximation here. And we can solve for X and get our pH out of it, right? So 1.5 molar solution of this, what we would consider a weaker base, right, would still give a pretty basic solution of 12.25, right? So the point is we have to pay attention when we have these weaker bases, right? So when you're doing this weak acid base stuff, pay attention to what your products are going to be. Strong acids, weak bases, right? Strong acids make weak bases which don't affect the pH. Weak acids make stronger bases which will affect the pH. Everybody with me on that one? That's the key part here, okay? Okie dokie. Oh gosh, zoom out here since I know there's a lot of yada 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 for you guys to write down here, right? But, so here's to kind of answer your question there, right? So what happens if we go in the opposite direction? What if we have a weak base and a strong acid? Well, what's going to be different here? Well, a weak base makes a stronger acid, right? And so then, after the acid-base thing happens, then we have to deal with the stronger, right? We have to deal with the stronger conjugate acid of our initial base. And then we go through and we write an expression for that. And when we write our expression, we get H3O+. H3O+ is hydronium, so we know our pH is going to be lower because we're making hydronium, right? That's all this is in, right? So this is the exact opposite of what we were just talking about, is all it is. Okay? Weak bases make stronger acids, right? Those acids are going to dissociate, make H3O+, change the pH of our final solution, okay? That's what this point is in here, right? If we do a neutralization reaction where we have an equal molar, right, we're gonna actually have a pH that's gonna be less than 7. Okay? So be careful about this idea of what a neutralization reaction is. Yeah.
Is it important to know why weak bases make stronger acids?
Yes, extremely important,
Why is that?
but not right now. It's extremely, extremely important to understand it. I'll talk to you guys about that in a little bit, okay? Is everybody with me on this? You guys starting to see where this gets a little bit tricky here? Understanding the relationship between acids and bases, weak and strong, and when and where the pH gets changed after you do the acid-base reaction. Okay? Strong acid, strong bases doesn't, not going to do anything different. Okay? We'll end up with a pH of 7 if you have an equal molar solution. Got it? If you have an equal amount of acid and base, your pH at the end is going to be 7. Because strong acids don't make bases that go on to react. Okay? But weak acids or weak bases make something that can go on to change the pH at the end. That's the tricky part of these problems. Okay? That's the tricky part of these problems. Because what do we have to figure out? We have to figure out how much of this gets made, and then we have to figure out how much of this gets made after we know how much of that exists. You guys with me in that one? So we're going to have to do stoichiometry and then do K stuff to figure this all out. Right? So we're doing our K stuff that we've been doing all along. Now we're just saying, hey, don't forget about stoichiometry ahead of time. Okay? What's up?
If you went to an equimolar reaction using an acidic solution, is that only referring to a weak base and a strong acid?
Correct. Okay? Alright, so that seems like a good place to pause here. We'll finish up the rest of this chapter on Wednesday, and then we'll start to go into some problems and that kind of stuff. And I will put a quiz up for you guys, okay?
Can you help me understand why when we start using KD values for weak acid-base chemistry and not our
Yeah, so you technically are, right? You're using, K can be used for anything. It's just, so the way that it's similar to how we're doing the approximation stuff, right? So if we're assuming something's a strong acid, its K is in the millions or thousands, right? So we assume it completely dissociates. There's zero, we assume essentially that 0 is going back, right?
Oh, I see.
And so it just simplifies, right? Basically our X gets dropped out there and we just assume 100% of it converts, rather than 99.99%, right? So in all cases, we're using X, we just leave the math off and make it simple, right? That's all it is. Yep.